Okay, good morning, everyone. Welcome to our chemistry magic show up here at SFU Burnaby. So my name is William, and let me begin by acknowledging that we are privileged to gather today on the unceded traditional territories of the Squamish, Tsleil-Waututh, and Coquitlam and Musqueam peoples. We thank them for having cared for these lands and waters since time out of mind and look forward to working with them in partnership as we continue to build this great city together. If you know whose territory you're currently on, please take a moment to reflect on this. And if you don't know whose land you're on, I encourage you to look it up and make yourself familiar with the indigenous peoples whose land you occupy. Okay, so here we have.
Hello, guys. Good morning. My name is James. I'm one of the instructors here at the Simon Fraser University. I teach mainly introductory chemistry here. As you may or may not know, Science Rendezvous is an annual Canadian national STEAM celebration that occurs across the country and not just here. Okay. The Faculty of Science here at SFU is thrilled to stage this year's event virtually through these live chemistry demonstrations, all from the comfort of your own home. We hope that you'll be able to join us next year in person, and hopefully this is your chance to connect with our Science in Action team as well. We are basically a group that does a lot of outreach with K-12 students and learn more about the magic show today.
Hello, good morning, everyone. My name's Calvin. Just a few house rules before we actually begin here. We'll be sending out a feedback survey at the end of today's session, and hopefully you guys can give us some feedback and let us know how we can improve or what you actually enjoyed with this show today. On your Zoom accounts, you can turn on the live transcription. So if you want a translation of what we're actually saying, you get a live transcription right on the bottom of your screen. You can turn that on. And if you have any questions throughout this entire period, just type it in the Q&A box. There should be a Q&A icon on your screen and lets you type in questions, and we'll try to answer as most of the questions as we see they come in. Now, this show will be recorded and it will be posted on our website after today, and so you can rewatch this as you like to. And we'll hopefully just last about an hour or so from now.
Okay, so let's begin let's move over here. So Calvin this morning drew for you guys what I think is a beautiful picture. I quite like it myself. Maybe maybe I should keep this after we finish this. And so science is all about observations and being able to describe what we're able to see. So, if I look at this, I see here, we can think about it's a rectangular sheet of paper. It looks crumpled. There's a little bit of texture on the paper itself, but overall, you might be feeling confused as to, hey, it's just this white sheet of paper. There's nothing really special about it. So maybe what we can do is we can perform some chemistry and some reactions and see if we can make Calvin's drawing up here. So if we look at what we have today, we have some water, we have some vinegar, we have some soap, we have some Windex. We have some Windex here. And so we think about what Windex is used for. We use it for cleaning windows and just cleaning our homes in general. So maybe we can use our Windex to clean Calvin's drawing and see if anything happens. So let's go ahead and spray some of this Windex onto Calvin's drawing. So let's see. Oh, we got a flower over here. And then, oh, it looks like you drew some words. So this is Calvin's drawing. Hopefully it was pretty good. So welcome to SFU. And we hope you guys all have lots of fun today watching chemistry and the different kinds of reactions that we can do. Okay, so now some of you may be wondering, gee, how did we do that? How did we take this white sheet of paper and we get this beautiful drawing from Calvin? So if we look at this again, we can think of, is this magic or is this just science? So if we come over here, Calvin has a flask of water. So it's just from the tap. And if we think about describing water, so you want to bring it up to camera. So let's look at what water looks like. We describe water, it looks like this liquid. It's clear because you can see right through it, just like the Windex, you can see right through it. And if we think about the color, it's a colorless liquid because it has no color. And if we look at what else we have, so he also has a special chemical. He can show it up on the camera. Maybe some of you guys at home can try and pronounce it. So give you guys a second. It's a very long, complicated name. So this chemical here is called phenothaline. So the pH sounds like a F at the very beginning. So phenothaline. And so if we describe this liquid as well, it's clear. The bottle might make it a bit hazy looking, but it's clear and it's colorless. It pretty much looks like water in this case. And so if we think, what would happen if we were to mix this phenothaline with our water, just our tap water? So if we think about what happens, we're mixing two things together, and we're gonna try to hypothesize or make a guess as to what will happen. Okay, so let's go to the poll. So there should be a poll where you'll be able to take a guess as to what you think might happen. So we're mixing a colorless liquid with a colorless liquid. All right, so we have a few choices here. We have red, orange, yellow, green, blue, purple, pink, and colorless, and so on. So take a moment and okay, so let's see who's right then. So Calvin is going to take our phenolphthalein and mix it with water. So let's see, our most voted option here is red. So 27% of you said red, and then there was some yellow, blue, purple, pink, white, and then 27% also said colorless. So let's see who's right. So, okay, let's mix those two together. Mix it up, mix it up, mix it up. Anything? Okay, looks like we have this colorless liquid. So we're mixing colorless with colorless and we get this colorless liquid as well. So if we think about what else we can mix, so we saw earlier that we sprayed some Windex onto Calvin's beautiful artwork. So maybe what we can do is also spray Windex into our colorless liquids. So let's do the poll again and let's see what you guys think will happen. So here we're mixing a blue clear liquid with this colorless liquid here. So think about what would happen if we mix blue with colorless. So again, we have the same options as before, and let's see what you guys think. All right, okay, let's see what you guys thought, and then we'll add our Windex in. All right, so We got some lots of colors. Looks like blue is our most voted option at 41%. So let's take a look. Calvin, do you want to spray some Windex into that for me?
Yeah, for sure.
Okay. Whoa, what magic. So here we mix the blue liquid with the colorless liquid and we get a pink color. You know, that's not what I thought I learned in school, but we're gonna go with it. So here we have a pink liquid. So our next question is, you know, maybe I'm not a huge fan of pink. I like that colorless more. So we can think about what can we do to make our pink color go away. I want that colorless again. So something really cool about Windex is we think about what it's made of. It's made out of water. We have some detergent in there, which is why we get soap. We have a chemical as well called ammonia. So ammonia is what we call a base. If we think about acids and bases, for acids, you might find in lemons like citric acid or any limes or oranges. So a base is just the opposite of an acid. So that's what we have here. So if we think about, you know, what could we make this go back? Well, maybe we can just add an acid, which is the opposite of our Windex here. So we can add like vinegar or lemon juice, anything like that. But, you know, I'm not a huge fan of just adding a liquid. Maybe we can try something different. So James over here has, what do you have here?
We have a special instrument. It's a special tool. We can't really find it in Vancouver anymore, not this type at least, because it's made out of plastic, but this is a straw. Okay, so what can we do with a straw? What do we love to do with a straw? Obviously, we want to be able to drink through a straw. So should I go ahead and drink this solution here? No, we never want to ever drink chemicals, right? At least, especially when you don't know what it is, okay? But instead, I can blow through the straw, okay? So we breathe out something, okay? So think about what we breathe out, okay? Is it oxygen? Is it carbon dioxide? Is it hydrogen? What do we breathe out, right? That's right, we breathe out carbon dioxide. So let's see what happens when I go ahead and put in some carbon dioxide here, okay? Watch very carefully.
Let's see, we got some bubbles going on as James is blowing some carbon dioxide into our flask. So remember, I want to get rid of that pink. I want that colorless liquid back. And it looks like it's working.
I got magic powers. Look at this.
We get that colorless liquid back. Okay.
Whoa.
Interesting.
What if we added some more Windex back in? What do you think is going to happen this time? You think it's still going to change? Let's see. So if I add a little bit of Windex, we got pink. Give it a little quick swirl. It's pink, pink, and whoa, it disappeared. So what this means here is that I got lots of carbon dioxide that I added in here. And carbon dioxide, when you mix it in water, creates a weak acid called carbonic acid. And that is what happens when it mixes in water. Okay.
Okay.
Now, Windex is also very useful in other types of indicators and papers, so to say. So what I have here is a special, what we call goldenrod paper. Okay, so it looks very plain and simple. It's just a sheet of paper here. Now we can add on Windex in there as well. Okay, so let's see what happens when we put Windex. What do you think is going to happen when I take Windex and I mix it in with this piece of paper? So shall we do another poll? Let's do it one more time.
Yeah, I guess we can do a poll this time. So we're mixing a blue Windex liquid with this yellow golden sheet of paper. Let's see what you guys think we get. Blue plus gold color. Okay, let's take a look at what you guys think. All right, we got green is popular, blue. We have some pink as well, is also popular. Okay, so let's see what happens then when we mix this blue with this yellow sheet of paper. Wow!
Look at that.
Literally, it says wow. So we get this red sheet of paper now when we spray a blue Windex.
So remember that Windex is something basic. So if I add something acidic, so what I have here in my hands is a solution of vinegar. And let's see what happens when I put some vinegar in there to mix it in. So notice that I managed to draw lines across here. Let's highlight our wow aspect of it. Look at that magic water, so to say. Okay, so we're changing the acidity of our solution on our paper, and that will change color. So it's a special indicator. Now we're going to show you another type of indicator that is really, really cool. It's magical powers of changing other colors.
Okay, so in here we have a graduated cylinder with just the same tap water that I filled up not too long ago. So we also have a different special chemical here. It's a bit easier to pronounce. Calvin, do you want to show them? So this one here is called universal indicator. If we look at what universal indicator looks like, it's this red liquid, nothing too special about that. So we think about what would happen if we mix red with our colorless water here. And so, I would imagine that if you mix red with colorless, then we would just get red. So let's go ahead and add in our red universal indicator, and let's see what happens. Oh, interesting. Okay. So in this case, it looks like when we mix red with colorless, we get this green solution. And I don't think that's what I learned in school, but that's okay. That's okay. We'll go with it. So let's see what other chemicals we have. Before with the phenothaline, we used Windex to make our solution pink. But in this case, I think Windex is a bit weak, so we have a stronger base here called sodium hydroxide, NaOH. So this is a colorless liquid, pretty much looks like water. So we think about what happens if we mix colorless with green. Let's see what happens. I would expect that colorless plus green gives us green. Oh, okay. Okay, so here we get this purple liquid. So apparently red plus colorless gives us green, and then green plus colorless gives us purple. Interesting. Okay, I mean, we'll just go with it. We'll go with it. So, just like before, maybe not a huge fan of purple. I really like green more. So I really want to get that green color back. So if we think about how can we make this go back? Earlier on with the phenolphthalein, James blew some bubbles. So maybe James can blow some bubbles again. But James, do you want to blow some bubbles?
No, I don't really want to blow that many bubbles.
Oh, really? Oh, okay. Well,
is there a faster way?
Is there a faster way to get carbon dioxide into our purple liquid? Is there?
I think so. I do have something here that's floating around. Okay. Anybody know what this is? It looks like it's an ice, but a gas is coming off. But there's no water or liquid that's coming off of it. right? You don't see any liquid dripping here, but it's super duper cold. It's about minus 78 degrees. This is known as dry ice. Now, it's called dry ice because it's dry, right? It goes from a solid to a gas. This is known as sublimation. Okay, it sublimes. It goes directly from a solid to a gas. Okay, and now when we put this in water, right, it will actually produce a lot of bubbles. Okay, and then we can kind of show you with just a dish of water here. And we're just gonna put this onto the side back here, and we can see and show you that it just basically produces bubbles. Okay. And we can see all this gas coming off. Okay. So as you can see here, you'll see a bubble inside. Okay, so carbon dioxide is being released here. Okay, so let's just see what happens if I was to add this into our tube here, or our graduated cylinder, we call it. Okay, and we add it inside to our solution. Okay, so here we go. Watch very carefully.
All right, I'm seeing a lot of bubbles forming. Looks like there's some white gas coming out. It's still purple. I really want that green color back.
So let's add a little bit more. Should we add more, guys? Let's add a little bit more. Everybody's saying more, 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 more.
I always like to add more. I really want that green color back.
All right, we can see a bluish color. Is it blue for
Okay.
sure? Maybe not quite. It kind of looks more green to me now.
There's the green I wanted. There's the green. What?
Ah, my favorite color is yellow.
What? But I want green more. Can we get that green back?
Maybe. All right, let's see what we can do here.
Okay, Calvin's gonna add some more of that sodium hydroxide, and we get that purple again.
There's a green.
Oh, there's my green I like. Purple, blue, green, purple. Oh, it looks like it's cycling a lot. Really just want that green, but you know, that's okay.
Is that magic, guys? No, it's science here. We're just playing around with some acid and bases. Now, I always like to do this as we're getting a lot of this gas coming off. Okay. Wanted to just put a little glove and just say hi to everybody. My little royal wave here. Hello, everybody. Hello. Look at that wave, guys. High five. High five. To everybody. All right. So, what do you think will happen then if I was to add some Windex back in there? Okay, so if I was to add some Windex here, remember that Windex is a type of base. It's also a detergent. It's used to clean stuff. So let's see what happens if I was to add some Windex. Watch very carefully. What do you see?
We got lots of bubbles.
We see bubbles. Look at this. Bubbles, bubbles. So inside, if we were to pop these bubbles, you can see that we got a lot of gas filled inside. And we're going to actually show you this again on a bigger scale, okay, making bigger bubbles. So let me just kind of swap this around here. We got actually two special dishes that we can use.
All right, let's see if we can make a big bubble here. So what I have here is put some more dry ice into our dish here. And in my little beaker here, I've got some soapy water.
Okay, let's see if we can try to make bubbles with carbon dioxide with our dry ice. So I'm just gonna try to get some soap over this. All right, let's see what we can do with this. Okay, so we're getting this bubble that's growing. So let's think about what's inside of this bubble. Is it just air? Is it oxygen? Is it nitrogen? Or is it really just carbon dioxide? We put some dry ice inside, which we know is frozen carbon dioxide. So in this case, what we have in here is just carbon dioxide gas. And we can even try to play with this bubble so we can bounce it back and forth between Calvin and I. So that's one thing that we can do with dry ice and bubbles.
Now we can show you a little bit more on how easy it is to actually play around with bubbles. So we have another container here on the side. You see that has all the bubbles here. We're gonna have a little container. It's just attached to a little tube ending here. We're gonna add in some carbon dioxide here. Okay, so just make some gas appear. So we'll just put it in the water here. And we're gonna kind of close it up, but one side is open. We never want to have it all completely closed off. Otherwise, we could potentially hurt ourselves, right? The pressure will build up. But you can see now, we get a stream of gas that's coming out. Now, this is not exactly carbon dioxide that you're seeing. It's actually more of the condensation with the air around here. So the water vapor, that's where it kind of shows you that kind of almost, I guess, color smokiness from here. So let's just add this to some soap and let's just see if we can blow in some bubbles here. So watch very carefully and we can let it actually sit onto our special gloves that we have. And look at that, we can actually play around with it. Look at that. Okay, these are special gloves that we have. But once it touches the surface of the table, it may or may not kind of pop. But if you disturb it a little bit more, it could potentially pop. Look at that. Okay, let's see that again. Let's see if we can stack these bubbles on top. Oh, not quite here. Let's try that again. Let's do two here. Can we juggle? You think we can juggle? Are we a good juggler here? Almost, not quite. All right, so here we go.
Okay, so I'm a huge fan of bubbles, but just watching individual single bubbles, I feel like isn't the most fun for me. So what I'm going to do here is in this container, I have an Erlenmeyer flask, I have some water, I have this green dish soap, just the same soap you would use to wash your dishes. And I have something called potassium iodide. So in chemistry, sometimes reactions happen very quickly, but some of them happen very slowly. So we use catalysts like potassium iodide just to be able to speed up our reaction. So here, what we're going to do is I have a beaker of hydrogen peroxide, and what we can do is we can make oxygen gas. So if I mix these two together, we can think about and watch what happens. We have hydrogen peroxide, and then we just have a little bit of liquid in here. Okay, so let me add it in. I'll give myself a countdown from 3, 2, 1. And we get all these bubbles, as you guys can see. So just from that small amount of liquid, we get a lot of bubbles. So this is something called elephant's toothpaste because we like to make lots of bubbles so that we can use it to brush elephants' teeth. Okay, so this is a reaction where we generate lots of oxygen gas as well as some heat as well.
Alrighty, so now let's think about what's in our atmosphere here. So in the air that we're breathing in, we've got different types of gases. We know that we personally need a lot of oxygen to survive, but the majority of the air is actually made out of nitrogen. Now earlier we looked into a carbon dioxide in the form of a solid, right? So with carbon dioxide we usually breathe out as a gas, but we can get it in the form of a solid as part of dry ice. Now, what we have here is something colder than dry ice. So remember, dry ice is about -78 degrees Celsius. What I have in here instead is about a -196 degrees Celsius. Now, this is made out of a chemical, right, called nitrogen. But instead of being gas like what we have in the air right now, this is actually called liquid nitrogen. And so what I have here is a special container to contain our liquid nitrogen. And I'll just pour some in and notice what happens when I pour the liquid nitrogen here. What do you guys see? How would you describe this liquid nitrogen? Well, from first looking at it, it kind of looks like just water, right? It's liquid. And it's also very clear as well, so you can see right through it. In this case, if we take a closer look at it, you can see that it's bubbling a lot. So it's kind of like it's boiling. But instead of boiling like water does, which boils at a very hot temperature, this liquid nitrogen boils at a very cold temperature at that -196 degrees Celsius. Now, obviously, it's very cold, and so if we try to throw something there, it might just freeze. But let's see if that is actually going to happen. So what I have here first is a tube. It's a rubber tube. We can see that it's very stretchy, and it is also very flexible as well, right? I can tie different knots onto it, and then I can also release knots. You can hear. What do you think will happen if I put this into the liquid nitrogen? Well, because it's so cold, it might just freeze. So let's take a look at what happens here. So notice that when I put it in, the tube causes the liquid nitrogen to boil because the tube is a lot hotter in comparison to that liquid nitrogen. But eventually, after some time, it will start to lessen the amount of boiling in there because the tube is just as cold as that liquid nitrogen. It's kind of settled now, but what we should be able to see now is that freezing that we kind of predicted earlier. And in this case, hopefully you'll laugh with me, this is a YouTube.
I'll laugh for you.
Thanks, William. We've got a YouTube here, right? And if you bang it to the side of the flask here, you can hear that it is pretty solid. Now, we can throw other things into this liquid nitrogen as well. William has kindly blown me a balloon here. We can see that it's very squishy. It's an orange balloon. Inside's just regular air. Now, what do you think will happen when we put this balloon into our liquid nitrogen? Do you think it'll pop? Do you think it'll grow bigger? Or what do you think will happen here? Let's see. We've got a poll going on here. So we've got a few options. Will it pop? Will it shrink? Will it expand? Or nothing will happen? Will it just freeze? Just like that YouTube. So take a moment just to put that on your poll here. And so let's find out, shall we? So I'll put this balloon here. Most of you, it looks like it's it might pop. Let's see. So here we go. I'll drop the balloon in. 1, 2, 3. And let's see what happens. So I might just help it push it down a little bit, but what do you notice so far? Anything happening to the balloon? What type of magic power is this? It looks like the balloon is it's getting smaller. It's shrinking. It's becoming wrinkly like a prune. I don't know if you guys heard that too. It's making a lot of noise. It's making a lot of crackly noises. But look at that. Look at the size of the balloon right now. Is this magic or what happened here? Now the question is, where did all of that air go? We can see that the balloon got smaller. Did the air leave the balloon? Or was there a leak in the balloon? Or what do you think happened here? Well, let's see what happens if I try to pull this back out and take it out of that liquid nitrogen here. Let's see what happens here. I'm not really doing much to it.
Well, that's a really crunchy sounding balloon there you have, Calvin.
Reminds me of some potato chips.
Speaking of potato chips, how about we make some banana chips?
Ah, well, look at this balloon here. It became all squishy again. But yes, let's make some banana chips, James. Do you have any bananas that we can use?
Yes, I just had some breakfast here. I think I got some banana peels. That might make some good banana chips. How about we toss it inside? Let's see what happens. Notice that it's boiling right now, okay? It's boiling. You see lots of liquid going to a gas, okay? Because you're putting in something warm into this very cold liquid nitrogen, about 198 degrees, minus 198. So let's cook it a little bit more, so to say. And let's serve it on this big dish here, shall we?
Looks appetizing.
All right, let's take it back out.
So one final process to make chips is to pretty much just smash them into small bits. So if we take a regular banana and try throwing it and smashing it, can we do anything about it? Nothing really, right?
But what about with this frozen banana then? 1, 2, 3. It all shatters. Here we go, James. Your chips.
Amazing. I will take this and serve our staff here.
Okay, and then we can also pour some of this liquid nitrogen out and we'll see what happens. So we have this colorless liquid that's very cold, and when we pour it out,
Wow, it looks like it's disappearing in water here.
exactly.
So since we're talking about disappearing water, so in this case, liquid nitrogen, notice that there's nothing here, no water on the surface. Here I have 3 cups. So let's do a little bit of a game here. Okay, you may have seen this before. Okay, so I have 3 identical cups. Okay, they're all the same. There's no holes. Gotta make sure I show you guys that there's nothing here, no leaks. Okay, and again, these are all pretty much empty cups here. Okay. And I'm gonna go ahead and add some water. So just regular water. I'm gonna pour some water in here. Okay, so quite a bit of water. And we saw on the table, there's no water here. So I'm gonna go ahead, watch very carefully. I'm going to pour some water into this first cup here. Okay, so that's my cup number 1. Okay, so that's number 1 here. Okay. Now, if I move this over and I pour it over, It's now in cup number 2. In the middle. Now, if I transfer this over one more time. Okay. It is now in the right-hand cup. Okay, so I'm going to ask you guys in a bit. Okay, I want you to watch very carefully. Which cup will it be in? Okay, whether it be number 1, okay, meaning far left here, the middle, or the right-hand side here. Okay, so left, middle, right. So we'll do a poll in a bit. Okay, so you got left, middle, and right. Okay, so we're gonna go ahead and mix this around. So watch very carefully. Okay, I'm mixing it around. So remember, think about where the water is. Keep track of it. It's going to get a little faster. Maybe I need an extra hand to mix it around. So here we go. Oh, no, we're still good. We're still good. We're still good. All right, so think about where it is now. All righty. So let's see if we can have a poll ready here. So we got the left, middle, and right-hand side.
So where is that water? Okay, so it looks like a lot of you guys think it's this right cup over here. So let's see who's right. So is it in that right cup, James?
I don't know. I guess we'll have to find out.
Okay, well, I don't wanna spill this water here. Oh. I guess it's not in this cup. So where else might that water be?
Maybe it's in the
Which one do you think, Calvin?
maybe the left cup.
This one? All right, let's see. So I'm gonna pour out some of this. Oh, I don't think it's in there.
It's not in the left cup.
It's nothing in here.
Then it must be in the middle cup.
I guess there's only one option left. So let's try to pour some of this water out. Oh, there's
Where
nothing
did it all
in here.
go?
There's nothing in here either. Where's the water?
I swear I put some water in there. Let me put some more water in there. So again, if I put it in the left cup, and now it goes into the middle cup, and then we move it over one more time, it should now technically be in this cup here, right? So if I shake it around and swirl it around, I still feel that it's inside here. Okay, but let's just see what happens now. Okay, where do you think the water is now? Okay, we know that it's on the right-hand side. So if we just did a quick kind of switch around. So William, would you like to do the honors of just switching it around again? But slowly for them, maybe this time. Okay, so we now see it's on the left-hand side. Yeah, so now let's switch it back to the right-hand side. Okay, so where is the water now?
Well, I would think it's this one on the right here, right? So let me just pour it out. Oh, looks like there's something that was in there, but not a lot of water. Is it in the one in the middle here? There's nothing in here. What about this one? There's nothing in here either. So what happened to our water? I thought James poured out some water. I remember seeing him do it twice. And I guess there wasn't. But then if we look inside, inside here, there's nothing in here. inside here, there's not really anything in here either. But then in here we have something. You might be able to see that. We have some kind of like slimy goo in here. So if I put my hand in this, you'll be able to see that we don't have just water anymore, but we have this slimy goo here. So it looks like all our water was absorbed into here. And so this is something cool that some of you guys may have used at home when you were younger. And it's something that's found inside of diapers.
So it kind of looks like a little small powder. Now, this is very similar to the powder that William has. And we're going to show you very quickly how much water this thing can absorb. Now, I can go ahead and add some more water. So again, if I pour some water in here, okay, and Calvin, if you want to do the honors and just add water to our powder here that you can find very similar to stuff in diapers. Let's see what happens when we add in water. Just add a little bit here first and let's just see, right? And keep adding it, keep adding it, keep adding it, keep adding it. And you'll notice that we've actually added quite a bit of water and I can continue to add water. It's absorbing up all my water here, okay? So here, very similar to what we have. So it's all absorbed up in terms of the water. And at the end of the day, this is just basically dry. Okay, notice that there's no liquid. Okay. So it's kind of like snow. Okay. And then we'll just leave that to a side.
Now we've talked about what's in the air, right? So we've looked into nitrogen with the liquid nitrogen, carbon dioxide, and the dry ice. But then, what do we actually need for fire to burn? Well, it needs the same type of gas molecule that we need to breathe, and it's oxygen that we need for a fire to burn. Now, what I have here is just a dish and a candle here. And what I'm going to do is try to light up the candle and make a fire or light up this candle here. Now, what I'm going to add to this little dish here is some water to the bottom. And just to make things seem a little easier to see, I'm going to add in some food coloring, just a little bit of green food coloring here. Now, the question is, if I try to cover this fire up, what do you think will happen to the fire or the flame? So let's make a prediction here. So just think about what will happen if I try to cover it up with my flask. Will the fire grow bigger or will the fire stop? As in it'll be extinguished. Well, let's try and find out, shall we? So I'll take my flask here, invert it upside down and cover up the flame. So watch carefully. See what happens to our flame there. Well, the flame has definitely gone out. There is no more fire inside our flask. But what do you also notice? We can see that the liquid water has gone up into the flask as well. Why is that? Well, remember, fire requires oxygen for it to burn. And so as that fire uses up the oxygen, it removes that oxygen space. And so the water has a chance to fill up that empty space instead. And so that's how we manage to get the water to flow up into the flask. Pretty interesting, right?
Okay, so on the topic of fire and flames, we usually think of things burning from a candle as being, it produces a bit of light, but we can also burn other materials in chemistry that can produce even more light. So in here, I have a strip of magnesium metal, which you may have heard of. And so magnesium, when it burns, has a really cool effect. So maybe we can turn off the lights and then we can burn our magnesium strip here. Okay, so I'm going to use my lighter here. And let's burn my magnesium. So as you guys can see, we turned off all our lights here, but the magnesium burns very, very, very brightly. It's almost like a wand that you might see a wizard or someone else use. So we can take a look at that again. We have our magnesium and it burns very, 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 very brightly, just like that. Okay.
All right. So that is all that we have for you guys today. We have a few more kind of hands-on activity you guys can kind of do later on. If you guys want to drop in at in a half an hour, there's a same Zoom link. Okay, you'll be able to, ask questions. It's more of a drop-in. We're going to show you some, things that you can do at home if you like to want to join us at 12 o'clock. Okay, so between 12 to 1, feel free to pop in. We got a few kind of at-home experiments that you guys can do. And if you missed the beginning of our show, don't be afraid. We can come back at 1:30. So there's another similar show at 1:30 p.m. today. Okay,
it's the same Zoom link.
Yeah. Okay, so thank you so much for attending this event. We hope to see you guys next year in person. If you enjoyed our workshop, feel free to let your school teachers know. We do a lot of outreach. We invite students to come up to campus and do some fun activities. We also provide virtual workshops right now, so let your teachers know. Contact SFU Science outreach at sfu.ca. So until then, we'll see you guys later. Thank you so much.
Thank you, everybody.
Thank you, everyone.